exactly how this stupid math joke goes, because I meant to do it last time. Okay, I think it goes something like this. Why can't you cross a mountain climber with, how does this go? With a vector. I guess it goes like this. Because you can't cross scalars with vectors.
That's good.
Yeah. I didn't make that one up, but
That was good.
This is, yeah, so it goes something like that. But anyway, okay. These are circles. These particular circles are centered at the origin. If you have linear terms in x and or y, this is also the equation of a circle, but its center is not at the origin. So a typical pre-calc problem is to complete the square and get the center and radius of the circle. This is all well and good, but again, we'll, for the most part, not always, but for the most part, work with circles centered at the origin, because if they aren't, you can translate and shove it back to the origin. Now, I do want to address the threes here. I didn't have any such thing there. Algebraically, what makes these equations of circles is that I have x squared terms and y squared terms. When they're on the same side of the equals, they have the same coefficients. Including sine. And, you know, anytime I'm talking like this, they're on the same side of the equal sign there. And that gives you a circle. Without the linear terms, its center is at the origin. With the linear terms, completing the square would tell you exactly where and all that stuff. If I have equations like this, it's an ellipse, which to my way of thinking is a circle. I mean, it's not a circle. It's a circle that somebody either squished one way or sat on, I don't care. For our intents and purposes, it's going to behave like a circle. So, but formally, these are ellipses. And what's doing that is I have x squared and y squared terms. The coefficients have the same sign, but different values, different magnitudes. They're not the same. This guy's centered at the origin. If there were linear terms, it'd be centered someplace else. Now, as far as ellipses go, if I look at them centered at the origin, You know, maybe they're longer up and down, maybe they're longer side by side. You can look for what are called the focus. There's two of them. You know, if you tack these 2 points down and put a string around it, it gives you the ability to actually draw a pretty good ellipse. There are formulas for these. There's things called eccentricity of the ellipse. I mean, there's a ton of stuff you can study with this. There's a lot of analytic geometry. We're not going to need that. You can, via knowing which of these coefficients is larger, know if it goes up and down more than side by side. You can simply find x and y intercepts. I mean, this is all stuff we can do, but mostly what I need is that's an ellipse, so that you know the general shape. Okay? Okay. And section 11.5 will go into that detail, and typically an analytic geometry book will as well. Okay. This type of equation gives a hyperbola. And in particular, because I have no linear terms, these are centered at the origin. Hyperbolas look like the following. They're not parabolas, although they may appear like parabolas. There are asymptotic lines that go through the origin that kind of govern the rate at which these things go out. Sometimes they're oriented up and down like this. Sometimes they go like this. If there are linear terms, they're translated over somewhere. Completing the square would pull them back. Depending on which of these is positive and which is negative, they're going to go up and down or left or right. Depending on their coefficients, you can get the equations of this line. And now I can't remember, I think there are points in here as well that will govern the geometry. All of this is important if you're going to be tracking something like planets. Well, I guess those are elliptical, but you know, there are all these geometry features. Mostly what I need is for you to be able to recognize. Now be careful, because I've got my square terms opposite sign. But be careful, because if it's written like this, it's going to appear as if the signs are both plus. But in fact, you want your square terms on the same side of the equal sign before you go determining pluses and minuses. Okay? Okay, so these are what are called conic sections. If I write this down, I have no idea what that is. Also notice that none of these examples have any mixed x, y terms in them. Most things you cannot possibly graph. I mean, I can't even graph a simple polynomial like this. I can't even tell you where the x-intercepts are. I can't even tell you how many x-intercepts there are. Certainly no more than 5, but you know, these things can be nasty to graph. No one's going to expect you or asks you to graph this. Even on a calculator, these things are a pain because calculators have this nice finite view string, and you never can get the entire picture of it. So what we're looking for instead are a set of good examples so that we can illustrate other stuff with those examples. And these conic sections are going to satisfy that. Okay? Questions here? Okay. We move then into the quadratic surfaces, so section 12.6. There's a whole bunch of these. Context counts. If I write x equals 1 on a number line, that's a single point. If I'm looking at this equation in 2 dimensions, it's a vertical line. Where I have complete freedom in y. In 3 dimensions, this gives me a plane, which I'm going to be lousy at shading in, but let me remind you, we will take x coming out of the paper, y and z are in the plane of the paper, and apologies to you guys, but I can't, I mean, you don't want me doing different stuff in the book, then life will really get confusing. So this would be the plane, and you know, I don't know how to draw this real good, but this is what I do know how to say. This is going to be a plane which is parallel to the zy plane, 1 unit out from the paper. When I test over the stuff that we're going to go through right now, I'm not going to ask you to draw these things. It's going to be matching. But keep in mind, words work really well. Okay, any questions? Y and z are allowed to be anything, so the plane extends fully along the y and up and down along z. If I write y equals 2x plus 1 in 2 dimensions, that's a line. Y-intercept of 1. In 3 dimensions, it's a plane. So again, let me draw x, this is y, this is z, and what I will look at is this line in the xy plane. So it's a line with positive slope. it's got a y-intercept of 1, and it goes back like this. Now, I mean, I'm not good. I'm not an artist. You get Tony, he'll draw you all kinds of beautiful pictures. I used to feel that was a big lacking, and then I figured, nah, it's better off if I can't draw everything, because that's probably where most of you guys are. You know, so this is this line, y equals 2x plus 1 in the x, y plane. And then I have complete freedom with z, and so I lift that line up and down along the z-axis. Is this okay? So it's like I've got my line here in the xy plane, and I just lift it up and down along, you know, along the z-axis. Is this all right? See how this goes? Okay. Y equals x squared. In 2 dimensions, it's a parabola centered at the origin. It looks like this. In 3 dimensions, I have complete freedom in z. My parabola comes out along the positive x-axis, and basically I take this shape in the xy plane and lift it up and down around along the z-axis. So this up now. So you get this kind of shape. So basically, it's like this along the z-axis. Does this make sense?
Yeah.
Okay, now.
Shouldn't it be open to the right? The top of it to the right?
Well, it's not open to the right. It's coming out of the paper.
He's saying, shouldn't it wrap around the y-axis?
Yeah.
No,
Instead of around the x-axis?
it's not wrapping around the x-axis. It's
Well, just the way it's folding, it has the x-axis in its vertex. Should it have the y-axis in its
this
vertex?
is the guy in the xy plane, right here. Okay?
I guess what we're looking at is that the parabola is up towards y infinity, positive infinity, and over there it's up towards x, positive infinity.
Am I doing this wrong?
It's coming at us. It needs to go towards.
I'm sorry.
It's
You guys are right. That's kind of the point I wanted to make here. Okay, so x, y, z. Okay. X's can be positive and negative, Y's must be positive here. And then I do this completely along the z-axis. Okay? I do. Okay, now, here's what I really need you guys to be able to distinguish. If I wrote y, well, let's say I wrote z equals y squared. It's still a parabola in 2 dimensions, but instead of going up and down along the z-axis, this is going to be spread along the x-axis. So, let's see if I can do this one correctly. So here's x, here's y, here's z. Z is always positive, so in the plane of the paper, this is my z equals y squared. And then what I want to do here is pull this up and down along the y-axis. So that's a lousy picture. Okay, let me back up here and try and redraw. Z equals y squared. So I've got this guy. There. And it's going to move up and down the x-axis. Each one of these becomes a parabola. All right? So one of the things I want you guys to be able to pick up is orientation. Okay? And you get a lot of these things that are going to be totally beyond my ability to draw. You can look at y equals sine of x, and in 2 dimensions, that's your sine curve, but if I don't have z specified, it's going to take that sine curve and up and down along the z-axis. Orientation, that's one thing. All right? Okay. Oh, actually, let's do this first. X squared plus y squared equals 8.
Oh, no, we're talking about spheres. Sorry.
In 2 dimensions, x squared plus y squared equals 8 gives you a circle, radius square root of 8. What do? Z isn't mentioned, so cylinder. Up and down along the z-axis. This one I actually stand half a chance of getting a sort of acceptable picture. If I looked at x squared plus z squared, or say 3x squared plus z squared equals 8. Okay, formally it's not a cylinder because of these coefficients not being the same, but it's an elliptical cylinder or a cylindrical, I don't know. You know, the book is going to give all these cutesy names to them. I will never ask you what the names are. But this does give you a cylinder. And this guy is wrapped around the y-axis. that okay?
It's going away.
Hmm?
Nothing extra.
And a cylinder, maybe I ought to put that in quotes, because the cross-sectional cuts here are gonna be ellipses, but to our way of thinking, ellipse is essentially a circle and nothing's different there. Okay. X squared plus y squared plus z squared equals 8. What's this give you?
A ball.
Yeah, it's a sphere. Distance formula in 3 dimensions. And it's centered at the origin. Its radius here is square root of 8. The one thing I would definitely mention is start taking a look at what happens when you look at cross-sectional slices. You just get circles. Okay, so if you cut it right down the middle, you'll see a circle, but even if you cut it like this, you will get a circle. It's a sphere. And if I did this,
Still roundish.
yeah, I think they call it an ellipsoid.
Like an egg.
Yeah. And which way is it farther? I don't know, I don't care. Figure out your x and y and z intercepts. No big deal, just, you know, it's the same basic shape. If you threw linear terms in, it would center it someplace other than at the origin, in which case you could just translate it back. Okay? So you guys all know how to find x, y, and z intercepts, and that is governed by these numbers. Notice that if you let y equals 0, say here, you have this. If you let z equals 0, you have this. And if you let x equals 0, so this is how I take these slices. If x is 0, I have this. And those are all equations of ellipses. And that's my fundamental shape, an ellipsoid, 3 dimensions. Okay? Okay. These are the guys that, now the book's going to give these things names. I don't care what the names are. But I want you to see, first of all, how I've written this equation. Look for keeping positives. And this won't be uniform, but I'm going to try and keep my positives in front of my squares. In particular, I really like 2 square terms of the same sign there. Both of them plus. On the right-hand side, if you take x and square it and add 4, you always get back a number which is
Positive.
positive may or may not be, the x is squared, but you add 4 to it, you can be more than positive you are. You add x squared to 4, I guarantee you, you are gonna get a number bigger than or equal to 4.
Oh, well, yeah.
Yeah, I mean, not a trick question. Okay, so let me look at a couple of things. Let's let x equals 0, in which case I have y squared plus z squared equals 4. That is a circle of radius 2. Let's let x equal plus or minus 1. I get y squared plus z squared equals 5. That's another circle, but it has a bigger radius. X is plus or minus 4. I get y squared plus z squared equals 20. That's a circle of even bigger radius. Okay, so when x equals 0, I'm sitting in the yz plane. I have a circle of radius 2. That looks like this. So that's this guy. When I let x equal plus or minus 1, I come out from the x-axis, or go into the x-axis 1 unit, in which case I get a bigger circle. I'm going to be sorry I made these circles so big. So let me try and make these circles a little bit smaller so that we do a reasonable chance of sketching a graph. Okay, so here is my circle of radius 2. Here is a bigger circle and a bigger circle. And I move farther out, I get yet a bigger circle. And a bigger circle here. What I'm going to get is a 3-dimensional shape, somewhat like this. All my cross sections parallel to the YZ plane are circles. It's kind of like that cooling tower in nuclear plants, but it's on its side. You guys see?
Yeah.
So how am I viewing this? I'm viewing this by seeing that my cross-sectional slices are circles. What I'm seeing here is circle of radius 4 or larger. See what I'm driving at?